This video is part of the MCAT chemistry video course. Subscribe if you like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about virtual one-on-one MCAT tutoring. In this video, we're going to cover resonance structures. So first, we're going to talk about how to draw them and how to spot them, and then talk about how they affect the hybridization of the atoms within the structure. To understand resonance, you first want to make sure that you're really good on Lewis structures, because what resonance is the multiple ways that you could draw a Lewis structure for the same molecule. First, we're going to look at this molecule here, and its Lewis structures are drawn below it. And if you're kind of unfamiliar with how we got the structures from this molecule, that's more of an orgo topic. I will say, though, anytime you see this C double O minus or CO2 at the end of a molecule, it is going to be this type of looking molecule. So you're going to have that double bonded O and then the single bonded O. We're not going to look at how you draw this Lewis structure, but just trust that this first image there, that is the Lewis structure for this molecule. And what happens with a molecule like this and with many other molecules is that you could also have drawn that Lewis structure. And either one of those would be totally valid, and you could just end up drawing either one of them kind of just by chance because you followed the Lewis structure rules, and both structures would follow all those rules. So both of these are called the resonance structures of that molecule. And what you want to practice getting good at is not drawing all of the Lewis structures just on your first go, but drawing one Lewis structure and then being able to find the resonance structures by following these rules that we have written out here. So our first rule is that you can never change the atoms' positions. So whenever you draw one Lewis structure, the connectivity and where those atoms are, you can't change that. And usually all of your resonance structures are going to follow the octet rule. So if you ever draw a Lewis structure and then you're looking for the resonance, a good rule of thumb is when you're looking for the resonance structure, just make sure that it also follows the octet rule. A notable exception would be if your Lewis structure already contains atoms that exceed the octet rule. And I would not really worry about what atoms these are because it's fairly low yield. If you want to look up an example of this, though, SO4 2- has resonance structures and the sulfur breaks the octet rule. I think by the time you test, if you're going for a really high score, you are going to want to know some of your exceptions. But I would just, at the very least, wait until you've mastered all the high yield stuff, and only then would I recommend going back and trying to memorize and look at the exceptions to the octet rule. But those atoms would be an exception to our resonance structure rules. And then another exception is that sometimes you're going to see atoms go below the octet rule. So they're going to end up having like 6 electrons in one of the resonance forms. And we'll look at an example for number 3 that breaks that rule. Lastly, when you are making your resonance structures, you're going to be moving electrons, and the movement of the electrons needs to follow one of these patterns. And that's going to be you're moving a lone pair to a pi bond, and then pi bonds will be covered in hybridization, so go back and watch that video. We're not going to talk about what those are exactly. And then you can also move a pi bond to a lone pair, and then you can move a pi bond to become another pi bond. And pretty much, not like every time, but pretty much most of the time, you're going to be moving multiple pairs of electrons at once. And we're going to see that in this first example that we'll go over with number 1. For number 1, let's say that you drew the structure on the left first, and then you're trying to find what the resonance structure would be. Just start looking at these 3 possibilities of how you can move electrons, and then see what you can do without breaking any octets. Let's look at what you could not do real quick, just so you can see. You could not take this lone pair here and try to make it become a pi bond between the O and the C, because that would give the C, the carbon there, too many electrons. The carbon would now be breaking the octet. So that is not something that we can do. If you look at the other oxygen though, you can move one of those electron pairs down there to form a double bond between the O and the C. And you might be thinking, okay, well now that C has too many electrons. But what we can do is move one of the pi bonds to become a lone pair on the oxygen, which then allows the carbon there, to not exceed the octet. So we moved a lone pair, and that lone pair became a pi bond between the O and the C, and then the pi bond we moved to become a lone pair. So we followed all of our rules. And the structure to the right of these double arrows, the structure to the right would be the resulting resonance structure after we've moved those electrons. So notice we have this pi bond here that was formed from the lone pair, and then here is our lone pair that was formed from that pi bond that we moved over. Underneath of it, we have written what is the true structure of the molecule. So at all times, the molecule is a mix of all the resonance structures of it. Now we'll look at number 2, which is a really, really important one because this is a peptide bond, and this is going to come up in a lot of future chapters as well. And in the middle, we have a lone pair that we could move to form a pi bond between the C and the end, and then that would push off a pi bond from the oxygen in the carbon to form another lone pair on the carbon. So then our resulting resonance structure on the right here, that oxygen has the third lone pair, so we can just arbitrarily choose one of those lone pairs. So there's that lone pair that came from one of the pi bonds, and then there's our new pi bond that formed from the lone pair on the nitrogen. And notice how on our second resonance structure on the right, that did create some formal charges. So on the oxygen, there is now a negative charge, and on the nitrogen, there is now a positive charge. So sometimes that does happen with resonance, as you do create formal charges. Below it, we have again drawn the true structure of the molecule, which is a mixture of those two resonance structures. And it's worth noting that not all resonance structures are going to contribute the same amount to the true structure. And what you want to look for is those formal charges that we just mentioned. So the molecule on the right, the resonance structure on the right, has 2 formal charges. So that lowers the stability of it, where the molecule on the left doesn't have any formal charges, so that is a more stable molecule. So our resulting structure, that the one on the bottom, tends to kind of look like the one on the left. So it looks a little bit like the one on the right, but it's mostly like the one on the left. And as far as like what percentage of each it is, you don't need to worry about that. All you need to know is that it'll be more like the one on the left than it is like the one on the right. Now finally, we'll do our last example for number 3, and this is one of those examples where we break the octet rule. And frankly, I would not worry about this maybe at all. I was pretty hesitant to even put it on the video because I really don't think you should worry about it. I just wanted to put it on here just to kind of explain one of those exceptions to those rules. So for this one, we have a pi bond becoming a lone pair, and that's all we do. And what that causes is, if you look at the resulting structure on the right, the CH2 lost that bond, and now it only has 3 bonds. So then it gets a formal charge, a formal plus charge. And then the other C now has a lone pair with 3 bonds, which gives it a negative formal charge. And formal charge was covered in a previous video. So if you want to see how to learn formal charge, then go back and watch that one. But now our structure on the right has 2 formal charges, and it's breaking the octet rule. So just like what we said before, both of these contribute to the overall structure of the molecule, but the structure on the left is far more favorable than the one on the right. Now we need to talk about how hybridization is affected by resonance. And here is a rule that we have written where an atom's hybridization will always be equal to its hybridization in the resonance structure that has the most unhybridized p orbitals. So what that means, we will dissect by looking at an example here. So let's pick just this top oxygen here and go back to the hybridization video if you need to understand what we're going to say here. But this oxygen has 3 electron groups, so that oxygen would be sp2 hybridized. But if you look on the resonance on the right side, it has 4 electron groups, so then you would think that it would have to be sp3 hybridized. But remember how in reality the molecule is actually a mixture of both of those structures? And in the structure on the right side, both of those oxygens have partially a double bond. And if you remember from hybridization, double bonds, one of the bonds in the double bonds has to occupy an open p orbital. So in order for these oxygens to have partial double bonds, they need to have at least an open p orbital. And that line is a line for the orbital, not a minus sign. So what that means is that even though on the structure on the right, it does look like it is sp3, it can't be sp3 because it does have a partial double bond character, so it needs to have the open p orbital. So it's not sp3, even on the structure on the right, it's still just sp2, which actually means one of our lone pairs is occupying that open p orbital, which that does go against something that we said in one of the hybridization videos about lone pairs always occupying the hybridized orbital. But whenever you have resonance structures, the lone pair, if that lone pair can also become a double bond in one of the resonance structures, then that lone pair electrons do occupy the open p orbital as well. This gets really important when you look at peptide bonds. And if you look at the structure on the left, the nitrogen looks like it's sp3, and then on the right, it looks like it's sp2. So what that means, by the same logic as before, is that it's never actually sp3, it's always sp2. So when you see this structure on the left, which a lot of the times the one on the left is how you're going to see a peptide bond drawn, when you see that one drawn, you have to remember that the nitrogen is sp2 hybridized, which means that there's a partial double bond there, much like how this one is drawn. And one thing about double bonds is that they don't rotate, which is really important to peptides, because if you take a bond in a peptide and it can't rotate, that's going to drastically change what can happen to it. So it's really important to understand how something actually being sp2 can change the behavior of that molecule, especially when you're dealing with something like peptide bonds. And just want to point out real quick that the other oxygen up here, that would also just be sp2 hybridized because of the resonance structure on the right. And then the oxygen in our peptide, that one is also sp2 hybridized because of the structure on the left where it's sp2 hybridized. And again, a lot of this will affect electron and molecular geometry, which will be covered in a future video.